Hello and welcome to another OpenStack RDO Hangout. Today, Eoghan Glynn will be talking about Ceilometer and what's coming in Kilo, and in particular, the new Gnocchi storage backend. So here's Eoghan.
Thanks, Richard. Hi, folks. So for those of you who don't know me, my name is Eoghan Glynn. I'm the PTL of Ceilometer. I have been so for the last 2 cycles. And I'm going to basically concentrate over the course of this Hangout on getting the word out on a major new development in Ceilometer. And that's basically an effective reinvention of how we store stuff in Ceilometer. And the intention here is for us to use this as our way of breaking free from a number of legacy issues that have held us back in the past. So this is basically work that's been done at arm's length from Ceilometer via a separate project called Gnocchi that was spun up by Julien Donjou, who's my predecessor as PTL of Ceilometer. And we've done it as a separate project so as to minimize the impact on the day-to-day of the maintainership going forward of the core of classic Ceilometer. But this is what we have our eye on as the future. And basically what I want to use this Hangout to do is kind of talk you through what the motivations are, what's different about Gnocchi compared to classic Ceilometer, and how we're mapping on various use cases that we have today onto the brave new world that'll be rebased on Gnocchi. So what's the exact problem that we're trying to solve here? So this obviously is the first thing we have to get clear as a kind of motivation for doing all of this work. So basically one thing that's at the core of Ceilometer that everybody who has peeked into the data store to any extent at all, or even looked at the response bodies from API queries, is that the sample model in Ceilometer is quite heavyweight. So every single sample that we store contains a bunch of free-form metadata. And this is kind of like a snapshot of the resource state as it existed at the time at which we took the measurement that the sample represents. So a sample in Ceilometer terms is really just a data point. Yeah. But in addition to this data point, we carry around a bunch of other information. So if you take, for example, a typical resource type, like say an instance, that resource metadata that we store alongside the sample would include things like what's the UUID of the image that this instance was booted from? What's the current state of the VM? What pieces of user metadata have been set on this instance? That kind of stuff. Now the thing is that this gives us a lot of flexibility in terms of composing queries on the Ceilometer metering store. But it also comes at a fairly hefty cost, right? And this approach basically has kind of been a legacy issue that's been around in Ceilometer from the very get-go. And the way I view it is, it was kind of an architectural misstep that was made at the outset. And we're basically grasping the nettle now to address it. And the reason we want to do so is that there's a few kind of unfriendly side effects as a result of this approach to storing samples with free-form metadata. For one thing, it leads to a fairly hefty storage footprint. So if you have a cloud of a certain size, a certain number of resources, and you have a certain cadence of metering configured in Ceilometer, you're going to basically fill up a lot of storage very quickly because the amount of data per additional data point is quite large. Also, the actual process of taking that information, transporting it via the AMQP bus, and then literally ingesting it into the metering store, into the backend database, that's suboptimal. That's more kind of time-consuming than it need be, given the fact that most of this free-form resource metadata is either A, completely static, or B, very infrequently changing. So, for example, the image UUID of the image that you booted an instance from, that's not going to change really unless you perhaps resize or rebuild the image. But in the normal course of events, it's not going to change. Other things change a little more often, say like the instance state. For example, you may suspend and resume an instance. But again, that's relatively infrequent. And storing that data over and over again that's either static or very infrequently changing is a highly suboptimal approach to gathering the data that we need. Another nasty side effect is that the actual API that we use for query doesn't scale particularly well if you have queries that match a large number of data points. Because in addition to the actual data involved, there's a large amount of noise in the background associated with the resource metadata that has to be stored and has to be managed by the underlying database. And it also gives us, this is kind of more of a purist objection, but it gives us kind of a weakly typed API representation. Because the resource metadata, they're effectively free-form dictionaries. We don't, in our API representation, have a rock-solid way of describing exactly the information that you'll get back if, for example, you query samples associated with an instance or an image or a volume. Yeah? So the actual resource metadata that we have depends sometimes on where we got the data. Did we get it from a notification, or did we get it from a polling action, for example? And that gives us a weakly typed API where it's not always predictable exactly the data you're going to get back if, for example, you emit a particular samples query. So that's really why we're attempting to attack this. Now, of course, having that free-form metadata available does give us a lot of flexibility as well. But it was our considered judgment, after having kind of lived with this over several cycles, that the additional flexibility that we get from storing this snapshot of resource metadata is really not worth the additional downsides that we've experienced. So that's why we're attempting to change our course, do this kind of course correction by adopting Gnocchi. So what are the key approaches taken by Gnocchi? Well, for one thing, the representation of resources in Gnocchi is much more strongly typed. We don't just say, hey, we have a resource, it's got some generic stuff like it's associated with a particular user and a particular tenant, and then it's got a bunch of things. Okay, so to return to the key approaches taken by Gnocchi. So one of the really central ideas here is that when we represent a resource in Gnocchi, that we do so via a strongly typed representation of that resource. So instead of just, as we do in classic Ceilometer, taking the generic aspects of the resource, and those being predictably present, such as a user ID and a tenant ID and stuff like that, and then having a big bag of free-form metadata data associated with that, instead we define upfront in the actual schema what data we store for each individual resource. So, for example, for an instance, we might want to store the display name for that instance. We might want to store some kind of grouping attribute that might be used by Heat for grouping together all of the instances that make up an autoscaling group. We might want to store the image UUID and several other things. But the key point is that these are defined up front, they're strongly typed, and they're always predictable that for every instance of a particular resource, that those particular attributes will be available. Now, what do we lose when we don't actually snapshot the resource metadata that we previously would have stored in classic Ceilometer? Well, we lose that ability to track the resource state timeline. Yeah? So basically the ability, for example, to say for a particular instance, it was active from this point in time to another point in time, then it was suspended for a while, then it was active again. But the point is that almost all of that resource metadata is either static, as I said before, or very infrequently changing. So rather than storing many snapshots of this pretty static stuff, instead, we just store much fewer events, and each of those events represents a transition in the resource life cycle. So, for example, a resource beginning to be resized, the completion of a resize, a resource being suspended, an instance being restarted, those kind of events that are relatively few and far between and are a much smaller volume of data to store than the continual repetitive snapshotting idea. So another thing that we do in Gnocchi is we're all about the pre-aggregation. So instead of storing all of the data in full resolution, what we do is as the data is ingested, we pre-aggregate it according to some configured granularities, and we call this the archive policy associated with the metric. So the archive policy basically determines at what granularity the pre-aggregation occurs and what level of retention, what period of retention there is for this particular metric. So one metric, for example, CPU utilization, basically is something that is usually only usable or useful or actionable for a short period of time. So you might want to store that at fairly high resolution, for example, per minute data, but you might only want to store it for a day or a week. Whereas some other type of data may be something that you might want to retain for much longer, but at a lower level of granularity. And that pre-aggregation, that is the aggregation of data as it's received, so rolling it up via various aggregation functions like averages, standard deviation, median, maximum, minimum, all of that kind of stuff. That's done as the data is received in Gnocchi. And the other thing we support is the ability to do cross-metric aggregation. So basically, this is the notion where we've got several resources that are associated in some way. For example, a number of instances that are part of an autoscaling group. And we allow the data points associated with the metrics, with a particular metric, like say CPU utilization, to be, for each of these instances, to be aggregated. So you can, for example, get the, excuse me, the average across the entire group. So changing slides now to slide 6, where I'm going to just do a quick compare and contrast between classic Ceilometer and Gnocchi. So these are the kind of key points of difference where what we've done up to now will change significantly, fundamentally, and for the better, we think, as we adopt Gnocchi. So under classic Ceilometer, as I said, and this is one of the most fundamental points, the sample model is quite heavyweight. We've got embedded metadata, and that resource metadata is effectively a snapshot of the resource state as it was at the time at which the measurement was taken. Gnocchi, on the other hand, stores time series data, because remember, the actual key data in each of these samples is really just 2 bits of information. You've got a timestamp, which indicates when the measurement was made, and then you've got an actual number, a floating point value. So these are 2 quite lightweight pieces of data, and these are data that there exists many efficient ways of manipulating them, libraries such as, for example, the Pandas analytics library in Python, that allows us to manipulate these data in very efficient and convenient ways. Okay, another kind of area in which classic Ceilometer doesn't give you many degrees of freedom is around its expiry policy. So we allow you to, excuse me, to set a global time to live period in Ceilometer. And that means basically you could say something like, for example, once sample data is older than 6 months, I just want it to fall off a cliff, right? So it exists in full resolution right up to 5 months and 29 days, 23 hours and 59 minutes. And then, boom, it falls off the edge of the cliff. Now, sometimes that's not exactly what you need, because the actual interest you would have in older data differs depending on what the semantic behind that data is. So one metric you might want to only actually keep around for a relatively short period. It's only useful when it's fresh, and then you want to throw it away. Whereas some other data, for whatever reason, maybe for regulatory purposes, you need to carry it for much longer. So Gnocchi basically allows you, gives you a huge amount of freedom in terms of how you set this up. So it allows you for each individual time series to make it configurable what retention policies to apply. So for one, you might want to say, I want to roll up this data per minute and I want to store it for a week. And you might say you can have multiple archive policies or multiple granularity / retention pairs within an archive policy. And you can store maybe a less fine-grained version of that data for a longer period. And then once that period is actually expired, you just discard it. Whereas another metric, you may have quite a different set of granularities and retention periods that you might want to apply. And the point is that Gnocchi doesn't force you to do this globally. It doesn't force you to do it across the board for all of your different meters, as it were. Instead, it allows you to do it on a per metric basis, which is very flexible. Um, Classic Ceilometer, in terms of aggregation, the approach that it takes is completely on the fly. So as the data is ingested, it's stored in full resolution. And that's the only format we ever store in Classic Ceilometer. So it's either present in full resolution or else it's expired and it's discarded. Whereas Gnocchi allows, and then basically if you do in Classic Ceilometer want to roll things up on a basis of periodizing per hour or per day, well then you emit a statistics query, and the statistics API in Classic Ceilometer does all of the aggregation that's required, for example, working out the average over each individual 1 hour period. It does all of that aggregation on demand. And if you were to emit exactly the same query a minute later, it would repeat the same aggregation. So it's always done on demand for each individual query with no caching or anything like that going on. Whereas Gnocchi takes the opposite approach. Instead, it eagerly pre-aggregates data as it's received. You can set up the retention policies and the granularities of retention or of aggregation in advance, as I said. And in addition, we support a number of aggregation functions out of the box, all of the usual suspects like mean, standard deviation, maximum, minima, count, sum, first and last, all of that kind of thing, median, percentiles even, we've added recently. And then in addition, there's a mechanism that allows the actual aggregation function to be loaded dynamically. So custom aggregators can be defined for Gnocchi, and these custom pieces of aggregation logic can then be loaded as stevedore extensions. And that was the approach taken, for example, for some implementing some additional aggregation functions like moving averages. Basically, that gives us a lot of flexibility to add more exotic aggregation functions going forward, but without incurring the cost of doing that pre-aggregation for in every single deployment. Okay, another thing to notice that you will actually notice about Classic Ceilometer, if you go and you sniff around the metering store at all, is that the storage of resources and samples is quite intertwined. Yeah, so especially in the MongoDB storage driver, the two things kind of, if you look at the history of some of the queries, basically the actual strategies taken to store resources and to represent samples, are quite kind of intertwined and are not cleanly separated. Whereas Gnocchi takes a very clean separation of the storage and data models for resources and time series data. So the actual resource data, there's a relatively small amount of that. That's stored via a SQL Alchemy backend, so you can store it in MySQL or Postgres. Whereas the actual time series data is stored in a specialized data store that's optimized for time series data and nothing else. Now, the canonical storage driver that we use is based on the Pandas analytics library layered over one of the object storage models that you can use in OpenStack. That would be Swift or Ceph. And the idea there is that basically, out of the box, Gnocchi will work against a pretty common or garden OpenStack deployment without requiring any specialized metric storage. But in addition, we're working on backend drivers for Gnocchi that'll work with specialized metrics-oriented databases like InfluxDB and OpenTSDB. But the kind of canonical storage driver is intended to work from the point of view of working in continuous integration and in proofs of concept and so on against a pretty standard OpenStack deployment, as long as you've got Swift or Ceph, or even it can actually even work over flat files. And again, not something that would be recommended except in the kind of smallest proof of concept or maybe a DevStack style environment. But again, it's intended to be as simple as possible for people to kind of pick this up and play with it initially. Whereas in a production deployment, you might choose to use, say, InfluxDB, for example, or you might want to use Swift or the Ceph driver. Okay, so some basic terminology. This is on slide 8. Okay, so what have we got here? The first class resources within Gnocchi. So clearly you've got a resource, right? And this can represent anything in your cloud. And these resources are strongly typed. So we've got a generic resource, but we've also got an instance resource and an image resource and a volume resource and all of the other things that you would expect. Then a metric basically is anything that you'd like to collect, any aspect of a resource that you'd like to collect data about. So a metric might, for example, represent some quality or something that you can measure associated with a resource for which you'll have a sequence of data points. And we refer to each of those data points as a measure. Now, the individual metric is identified by UUID, or because the metric is associated with a resource, it can be identified by a string name, a more human-readable, human-friendly string like CPU util, combined with the resource ID, and you can use that to construct the RESTful path, as it were, to identify that particular resource. And then, as I said, the measure is just a single data point. And each of these is incredibly lightweight. These are feather-light compared to the relatively heavyweight samples that we use in classic Ceilometer. And they're composed of only a timestamp and a value. So these things can be stored in full resolution fairly efficiently. And of course, they can be distilled and aggregated and sliced and diced in lots of different ways, which is all much more lightweight than would be the case comparing to the traditional samples that Ceilometer maintains. Okay, so moving on to slide 9, further with the Gnocchi basics, we've got this concept of an archive policy. So an archive policy is basically the piece of data that effectively determines to what extent you store data, in what granularity you store data basically, and for how long you do so. So typical examples might be, say, 1 second resolution over the course of a day. So the last day's worth of data is stored, and at most 1 data point per second. Yeah. Or a less fine-grained alternative might be, say, 1 hour resolution over the course of a year, or even both for a particular metric. So each archive policy is composed of a set of retention and granularity pairs. You can have any number of these for an archive policy, 1 or more. And then the actual archive policy creation, that logic is an administrative function. So Gnocchi itself will come with a number of basic archive policies like high, medium, and low, excuse me, in the out-of-the-box form. And then an administrative user can go and add new archive policies over time as required. Aggregation, as I said, that's simply the function that's used up to roll up the data. These are continually running as data is ingested. And you've got all of the usual aggregation functions that you'd expect. So we've got a match for all of the aggregation functions that we have in classic Ceilometer. And in addition, we have some new ones like percentile and median, things that we don't represent in classic Ceilometer. And then retention basically is, as I said before, simply the idea that we store data at whatever granularity for a defined amount of time. And the degree of freedom is per metric. Now, in reality, what you probably do is group your metrics such that you would have one group of kind of fairly high granularity and maybe a short retention period. You'd have another group of metrics that would have maybe a longer retention, but also a less fine-grained granularity. And you would kind of balance things off on a metric per metric basis in the most extreme case. But you probably, in reality, only want a few different flavors of this. And so you'll have one bucket of metrics that basically you keep for a short time at a fairly high resolution, another bucket of metrics that you keep for a longer time but a lower resolution, and you balance things up in that way. So here's a picture which basically is intended to kind of represent the process of aggregation under Gnocchi. So if you look up to the top right-hand corner of that, that's basically intended to represent the here and now. And what we have in terms of that green bar is basically a buffer, a kind of a back window of the original kind of full resolution, non-aggregated data points. Yeah, and we store these as they arrive in the full resolution. The width of that back window, for example, in this case, there's an additional data of 1 hour. That's configurable. That's part of the archive policy. So you can say, hey, I want to keep 1 hour of full resolution data, or I want to do it for a full day, for example. Yeah. But the point is that basically, as this data is received, it's effectively immediately distilled down to a number of progressively less fine-grained granularities. The actual granularities that are used depend on the archive policy associated with the current metric. In this particular case, let's assume that there are 3 different granularities defined for this archive policy: 1 second, 1 minute, and 1 hour. Yeah? So as the data basically is being ingested, the data is kind of, I suppose, propagated down from the green bar, which represents the full resolution back window, down to the pink, blue, and orange bars, which represent the data that's aggregated at progressively coarser grain. Yeah? Now, each of these aggregations happens independently, so we don't have any mean of mean issues going on. So we, for example, aggregate down to 1 second, and then we take the raw data, and then we independently aggregate that down to 1 minute, and then we also return to the raw data to independently aggregate down to 1 hour. So it doesn't propagate through going to 1 second first, and then we take the average of the 1 seconds, and then down to 1 minute, and then take the average of the 1 minutes, and then to 1 hour, because that can lead to distortion effects, where you take the mean of means and the number of contributing data points, it differs from each bucket, from each period to the previous one. So that's basically all going on in the background as the data is ingested, as we receive it from the Ceilometer collector and store it in the Gnocchi data store. Okay, so basically moving on further to slide 11, just talk about a little bit about what we call the indexer in Gnocchi. Yeah. So obviously the purpose of Gnocchi is to capture measurements for different metrics. I mean, that's the main point of this whole thing. But in order for these metrics to actually have some meaning, in order for us to associate them with something in the real world and reason over these data and make decisions on the basis of these data, we need some kind of resource association. Yeah? Now, resources in Gnocchi obviously have strongly typed attributes, and this strongly typed attribute has to be schematized and stored somewhere, and that's where the indexer comes in. The indexer is the piece of Gnocchi that's responsible for storing the representation of resources. Yeah, the schema for the indexer basically will tell you for each individual resource what strongly typed attributes we store, and in addition, a resource to metric association is maintained. Now, when we started doing this first, obviously we wanted to have as much maximal flexibility. That's always the case when you're starting something new, a greenfield thing. And originally, we designed this, or Julien designed this, so that basically there could be a many-to-many association between resources and metrics. But in reality, we found that this actually added some complexity, and it was totally unneeded. So the newer versions of Gnocchi basically has a slightly simpler model, whereby the resource to metric association is one-to-many. So one resource can be associated with many metrics, but each individual metric is only associated with a single resource, yeah, because it's a set of data points about an individual resource. Now that association is keyed by name, yeah. So simple human readable names like CPU util, for example, or volume size, or disk read packets, or whatever it is, basically is used to key that individual metric within the scope of a particular resource. Yeah, and then if you have a loosely associated group of resources, for example, a bunch of instances, so the resources are of the same type, and those resources have some kind of defining quality. For example, they all have the same value for their server group attribute, which would be the case if these resources were, or these instances were all spun up by heat as part of the same autoscaling group. Well, then the measures, the data points associated with this set of metrics can be cross-aggregated. So you can construct a URL for the REST API exposed by Gnocchi and say, give me, for example, the average of all of the CPU util metrics associated with all of the resources that have a particular value for, we'll say, the server group attribute. And that would be the type of query that would underpin the alarm evaluation that would be used to trigger auto-scaling actions. So we can detect when the average CPU utilization across this set of instances tells us that the instances are overworked, that they're running hot, and that they need to share the work over a larger group of instances. So we need to spin up new members of the group, and vice versa. We could have another alarm that's based on a very similar Gnocchi query that basically tells us, hey, the set of instances are kind of running idle, they're underworked, so we can safely spin down some of the instances within the autoscaling group and still manage that workload to the extent that we need. Okay, so the Gnocchi indexer is I suppose the piece of Gnocchi that's responsible for this. And I suppose why am I kind of laboring this point, which seems pretty simple? Well, I guess the key differences, the key change in mindset from the point of view of understanding the internals of this is that the indexer is a separate component in Gnocchi. So basically, Gnocchi can use two different storage drivers, one for storing the resource model, right? So that would be the indexer piece. So it would be a representation of each of the resources that we know about, yeah, and then a mapping between the resources and the metrics. But the actual time series data that's stored for the metric itself, yeah, these are stored in specialized time series data storage that basically allow that type of data to be manipulated very, very efficiently. Okay, so moving on to actually some of the slide numbering is a little bit off here because I reused a slide deck that I'd used for a slightly longer presentation, and I kind of pared it down. So this one is labeled slide 18, but obviously it's not the 18th slide we've looked at. But basically, I just wanted to cover some existing Ceilometer use cases and how, excuse me, how these are going to map to Gnocchi. Because clearly, the approach that we took previously of storing snapshots of resource metadata, I mean, while it was very expensive to do so, it did give us a lot of flexibility. So the point is, how are we going to kind of continue to address all of the same use cases as we previously had using the Gnocchi model as opposed to classic Ceilometer? So a key issue that we're concerned with would be that we could continue to have Ceilometer alarming driving heat autoscaling. So heat autoscaling is, I suppose, the motivating use case for Ceilometer alarming. That's the reason why we actually support the alarming feature. So clearly we didn't want to break heat and leave that high and dry. So basically we do continue to support that. And basically we use two key aspects of Gnocchi to make it happen. One is the ability to do cross-entity aggregation or cross-metric aggregation. And second is basically the ability to store strongly typed attributes associated with an individual resource. So in our modeling of the instance resource in Gnocchi, we include a attribute called server group. And server group would generally be unset, it would be set to null or nothing. But in the case of an instance that's spun up as part of a heat autoscaling group, heat will cause that value to be set by setting some user metadata, by effectively tagging each of the instances that it spins up. So as far as heat is concerned, it's very similar to what went before, except that instead of that user metadata on the instance feeding into some free-form resource metadata snapshot on a heavyweight sample in the classic Ceilometer data store, instead it'll lead to a much more lightweight server group attribute being stored in the resource, and only one copy of that being stored in the Gnocchi indexer, as opposed to many, many, many snapshots of exactly the same data being stored in the heavyweight samples. Okay, so another thing that's obviously an important use case and that derived from this resource metadata snapshotting approach was the ability to reconstruct the resource state timeline. So that's basically the set of the set of transitions that the So that's basically the set of transitions that the resource will go through over time Now, previously, we would have derived that from the resource metadata snapshots, but instead what we're going to do is rely on our ability to store events. Now, events basically are just the distillation of notifications that we receive from the OpenStack services. Basically, and instead what we will do is we will issue queries over these relatively infrequent events to capture the state transitions. So for example, if you want to determine when a particular instance was resized, instead of basically having a query that that goes through a lot of sample metadata, which is largely unchanging, instead you can go through much smaller volume of data that basically represents the relatively few and far between events that capture those key transitional points in the resource state timeline, as opposed to the large, long periods of inactivity in terms of changes to the resource state. So that's a much more efficient way to store it, and also a much more efficient way to query it, because the volume of data being queried when we store things in the form of events, as opposed to snapshots of resource data, is orders of magnitude smaller. Now, one common criticism that basically is often leveled is the whole reinventing the, this is existing technology. There are time series databases out there. Why are we reinventing the wheel? So basically, I suppose the point is that we're not reinventing the wheel. We have specifically designed Gnocchi from the get-go to be pluggable. So to have the ability to take some existing metrics-oriented databases like InfluxDB or OpenTSDB and allow them to be leveraged by Gnocchi's pluggable driver model. And we're actually actively working on drivers at the moment for InfluxDB and OpenTSDB. Now, Gnocchi itself does provide an out-of-the-box canonical storage driver that I mentioned before. It is based on Pandas and Swift. It can be set up to work over Swift or Ceph, or indeed even over flat files. And the purpose there basically is to have Gnocchi, excuse me, be workable out of the box against a fairly standard OpenStack deployment. Okay, and basically in the case where we are using a specialized time series database, well then in that case, Gnocchi does have some work to do around managing the resource to metric association, and also managing the archive policy concepts, the ability to create a new archive policy, and then interfacing between that kind of that high-level abstract view of archive policy and the specific downsampling or distillation mechanism that the particular metrics-oriented database supports. Okay, so that's pretty much all I have to say about Gnocchi. I hope over the course of this Hangout you got a better view of A, why we're doing this, and B, what exactly we are doing. It's still a work in progress, so the intent is in the Kilo timeframe to basically have the distributions such as RDO and other distributions that consume the upstream artifacts to basically continue to support classic Ceilometer as the default out of the box, but to have the Gnocchi integration in a kind of a tech preview mode, so that people can kind of play with it and get to know what additional strengths it provides. But the actual classic Ceilometer approach to do things will be maintained for a very long deprecation path. So it's not going away anytime soon. We're not going to be pulling out the rug from under any existing users. But Gnocchi will be available as an alternative in kind of tech preview mode, so that we can get more detailed feedback, and people can try it in proofs of concept and so on. So that's all I've got to say. I will stick around for a couple of minutes and see if there's any further questions that people want to ask. I believe the standard channel is Audio Hangout. So I'm going to stay on that for a couple of minutes. I believe the Google Hangout is often out of sync by a couple of minutes. So we'll see if any actual questions pop up.
Well, I guess if there's no questions, we'll wrap it up. Thank you very much, Eoghan.
No problem. Okay, see you folks.